Hello and welcome back to the second part of the YOLO family. And in this video, we're going to talk about YOLO v2, and it also includes YOLO9000, better, faster, and stronger. The topics covered in this video is why do we use YOLO v2? And in the second section, we're going to discuss how does YOLO v2 work. On the third section, we're going to compare YOLO v2 with other methods. And finally, we're going to look at YOLO9000, better, faster, and stronger. So why do we need YOLO v2 if YOLO v1 has everything that we need? Clearly, YOLO v1 performed a lot faster compared to other methods, but its detection suffered by at least approximately 10 MAP compared to faster RCNN VGG16. And as we can see from the table, when we use a VGG16 backbone for the faster RCNN, we get a mean average precision of 73.2. And for YOLO, we actually got 63.4, and it's lagging behind in terms of accuracy from the RCNN family. And YOLO v1 makes a significant number of localization errors. Furthermore, YOLO v1 has relatively low recall. So the authors focused mainly on improving the recall and the localization error while maintaining the classification accuracy. So this is one of the motives behind the second version of YOLO, which was introduced in late 2016. YOLO v2 outperforms all the other methods in both speed and detection during that time. And at 67 frames per second, YOLO v2 gives a mean average precision of 76.8 on the Pascal VOC 2007 dataset. And at 40 frames per second, YOLO v2 gets a 78.6 mean average precision. And when you compare it with YOLO v1, which gave a mean average precision of 63.4 for 45 frames per second, that's a lot of improvement, and it's even better than the faster RCNN on VGG16 backbone. So how does the YOLO v2 model work? Computer vision generally trends toward larger and deeper networks if you want to improve the detection accuracy. So for example, if you want a better performance for your model, you have to create a model that is very deep, that's larger, and the resolution of the input image also needs to be increased so that the detection accuracy can be enhanced. And you can also include an ensemble of multiple models together in order to push that accuracy further. But the drawback of this kind of method is when you increase the size of the model, you're going to need higher computation in order to perform the convolutions, and the speed is going to be reduced significantly. However, with YOLO v2, they wanted a more accurate detector that's still fast, and instead of scaling up the network, they simplified the network to make the representation easier to learn. So they used a better approach. Instead of just increasing the number of layers to push the accuracy, which is going to reduce the speed of the network, they used a different approach. So we're going to take a look at how did they improve YOLO v1's performance. So the first thing that was introduced in YOLO v2 that wasn't included in YOLO v1 was batch normalization. As you know, in deep learning, Batch normalization was invented after YOLO v1. So when the authors wrote the paper of YOLO v1, batch normalization wasn't invented. So they just used a dropout layer instead of batch normalization during that time. So in YOLO v2, they added a batch normalization after every convolutional layer in YOLO v1, and this itself resulted in a increment of 2% in the mean average precision. So it gave them a boost in the mean average precision just by introducing batch normalization. And what is batch normalization? It just improves the model convergence by regularizing the inner layers. So let's take a look at what batch normalization does. So for example, in this network that you're looking at on the right, if you have an input, these inputs need to be normalized before you put them inside the network. For example, they can have a range of values. For example, for the first input, the range might be between 1 and 1000. And for the second input, the range might be, let's say, between 0 and 1. And if you introduce an input into the network that has a very large difference in terms of their range, it's going to cause what's known as exploding gradients, and that's going to reduce the performance of the model. So we need a normalization technique. There are a bunch of normalization techniques we can use. For example, you can just subtract the mean and divide by the standard deviation. Then you can normalize those values. But that's for the input layer. But if you want to solve the exploding gradients problem, some of the weights, for example, if they have larger weights, it's going to propagate through the inside of the network to the next layer until we reach the final layer. So if you want the weights, so the weight of the next layer is going to be dependent, the activation of the next layer is going to be dependent on the weights of the previous layer. So before you fit in that input into the next layer, you need to normalize that weight. So that's going to reduce the exploding gradient problem. And batch norm is just basically a normalization of weights in the inner layers of a neural network instead of the raw data. And it's done along mini batches instead of the full data set. And in the image, it's represented as a red line, and it's applied to the neuron's output just before applying the activation function. So usually a neuron in a neural network is going to use, without a batch norm, we can use the formula z is equals to, we put an activation function. No, we just use weights and the input features, and then we're going to add the bias. And then finally, we apply the activation function. So when we apply, here in this case, G is just a linear transformation of the neuron, and W and B stands for the weights and the biases, and A stands for the activation function. And the activation function can be a sigmoid function or any kind of activation function. But how do we introduce and incorporate batch normalization in the inner layer? So adding a batch norm means before we apply the activation function, we're going to subtract the mean from the output of the linear relationship between the weights and the input features. And we're going to divide by the standard deviation. And we're going to multiply that by a parameter called gamma. And we're going to add another parameter called beta. And that's just batch normalization. And then we feed the output Zn, which is going to be the output of the batch norm, onto the next activation function. And we apply the sigmoid function. And here we have to note that the bias of the neurons is removed from Z. Initially, Z equals to the linear function of Wx plus B. but since the mean is going to be subtracted from z, and it's going to the constant values such as b are going to be removed when we subtract the mean. So it's going to be subtracted by itself. So we don't need to introduce the bias, and it can be ignored when applying the batch norm function. Now let's take a look at the architecture or the backbone used in YOLO v2. So to solve the problems of complexity and accuracy, because we have mentioned before, when you build deeper models, the accuracy increases, but the complexity is going to also increase, and it's going to reduce the performance of the model. The authors proposed a new classification model known as DarkNet19 to be used as a backbone for YOLO v2. And DarkNet19 has the 19 part of the name was given because it has 19 convolutional layers and 5 max pooling layers. And 11 more layers were used for object detection. So in total, we have 30 layers. And it achieved a 91.2% top 5 accuracy on the ImageNet dataset, and which is better than the BGG model, which gave just a 90% of accuracy. And the YOLO network, YOLO v1 network, gave us a 88% just only for classification, because ImageNet is not used to train for detection. So we just only compare their classification performance. So this backbone has been proven to be better than the one that's used in YOLO v1 by giving a higher accuracy. So how did they train the YOLO v2 model? One thing they did was using a high resolution classifier. In general, object detection, we pre-train the model using the ImageNet for classification. Then for detection, the network is resized to a higher resolution, especially to detect smaller objects in a scene. Because YOLO v1 is not very good at detecting very small objects unless you use like a finer grid, and the resolution of the image wasn't that high, so we cannot detect smaller objects. Because when we talked about the structure of YOLO, we said that smaller objects are going to be detected on higher resolutions, and larger objects are going to be detected on smaller resolutions. And the original YOLO was trained as follows. So first, they trained a classifier network with a 224 by 224 input size. Then they increased the resolution to 448 and trained for detection. That's what they did on the original YOLO v1. So they just trained the classifier on 224 input resolution. Then they increased the resolution to 448, and they trained it for detection. This means when switching to detection, the network has to simultaneously switch to learning object detection and adjust to the new input resolution. So when you train the classifier, and then when you just train, when you simultaneously switch to train the detection, the model has to adapt itself to detection and to the new input resolution. But for YOLO v2, they initially trained the model on images at 224, and then they fine-tuned the classification network at the full 448 by 448 resolution for 10 epochs only on the ImageNet before training for detection. So on YOLO v1, they trained the model using the input resolution of 224, and then they trained the model again using the 448 input resolution for detection. But here they just trained and for classification by using the input resolution 224. Then the full 448 was just trained for 10 epochs on ImageNet before training for detection. So the higher resolution is also used for training the classification, not the detection. This gives the network time to adjust its filters to work better on higher resolution inputs. And this higher resolution classification network gives an increase of almost 4% of mean average precision. Previously, the batch normalization gave it a boost, and then now, just by applying a higher resolution, we can detect smaller objects and the finer details more closely, and it gave a boost of 4%. So the model was first trained on classification, then it was trained for detection. So when they trained for classification, the Darknet 19 network was trained by using the ImageNet 1000 class classification dataset, using the 224 input resolution for 160 epochs. After that, they fine-tuned the network at a large input size of 448, just for only 10 epochs. And this gives a classification accuracy of 76.5% and a top 5 accuracy of 93.3%. Now, next, after they have finished the training procedure for the classification, they just train the network for detection, and they only fine-tune the model. As we can see from the image, the third one is fine-tuning on detection. And after training for the classification, they removed the last convolutional layer from the Darknet 19 because that's used for classification. And instead, they added a couple of 3x3 convolutional layers and also a 1x1 convolutional layer, and with the number of outputs they need for detection. So for detection, we need a 13x13 grid, and 125 will be the number of channels. And we will see why the output of the YOLO V2 model is like this, because on YOLO V1, the output was 7x7, and then we have 30 for the prediction of the bounding boxes. And also a pass-through layer was added on the Darknet 19 so that their model can use fine-grained features from the previous layers. Don't worry about the pass-through layer and the fine-grained features. We'll talk about it on the next slide. Then they trained the network for 160 epochs on detection datasets, such as VOC and COCO datasets. So previously it was trained for classification, but then they trained the network for 160 epochs using object detection datasets. Now they're using the VOC and COCO instead of the ImageNet, because ImageNet is intended for classification, and VOC and COCO datasets are used for training an object detection model. So we said that they introduced a fine-grained features in the backbone of YOLO V2. So what does it mean? YOLO V2 predicts the detections using the 13x13 feature map. So on the original YOLO V1, we used a 7x7 feature map, but here we're going to use a 13x13 feature map. This is sufficient for identifying large objects, but not smaller objects, because it's not that large enough. It's going to identify large objects because their resolution is small, but it's not going to identify smaller objects. So to better localize smaller objects, a pass-through layer that takes features from an earlier layer at 26x26 resolution is concatenated with the low resolution features. So as you can see from the image on top, we used when we reach the layer that has the dimensions 26x26x512, we're going to introduce the pass-through layer. First, we're going to introduce a pooling layer and then reduce the dimension to 13 by 13 while the number of channels are preserved. Then we introduced a bunch of convolutions, and with the spatial size is going to be maintained, but we're going to change the number of channels to 1024. And then finally, we're going to have a 13 by 13 by 3072. Then the pass-through layer is going to take the 26 by 26 by 512 and reshape it into 13 by 13 to 2048. And then we're going to concatenate the output from this one together with the 13 by 13 by 3072. And that's all, because here we're going to concatenate the 13 by 13 by 1024 with the 13 by 13 by 2048, and we're going to have an output of 13 by 13 by 3072. And when you concatenate the 26 by 26 feature maps information with 13 by 13 feature map information, then you're going to better localize those smaller objects because you're getting some information from higher resolutions. And this gives a 1% increase in performance. Another technique that they introduced was a multi-scale training. So to make YOLO V2 robust to running on images of different sizes, they trained the model for different input sizes. So instead of using just the original 448 by 448, we can use different input sizes. So since the model uses only convolutional and pooling layers, the input can be resized on the fly. Because if you have a fully connected layer in your model, you're not going to be able to change the spatial dimension of your image. If you change, you need to remove the fully connected layer because that's dependent on the input. Since most of the architecture of the YOLO V2 model is just convolutions and pooling layers, you can just change the resolutions of the image without affecting the model. YOLO V1 used an input resolution of 448 by 448 for the input. In YOLO V2, they resize the input image randomly to different resolutions between the range of 320 to 608, and the resolution always has to be a multiple of 32. And we can talk about this, why they use a multiple of 32 when we talk about YOLO V3 in detail. And this multi-scale training can be thought of like augmentation. And it forces the network to learn to predict well across a variety of input dimensions. And this increased the mean average precision by 1.5%. Because when you use a multi-scale training, it adds an effect like augmentation. Augmentation is just a technique used in deep learning in which you augment and change either the resolution of an image, or maybe you use some translation, or you use rotation, different types of techniques, so that your model can adapt and learn when the input feature changes. So here, the augmentation, the kind of augmentation they used for YOLO V2 is just the multi-scale training. And when you use different input sizes, you're going to better detect objects at different levels, because smaller objects can be detected on higher resolutions and larger objects can be detected on lower resolutions. So the main concept that was introduced in YOLO V2 was anchor boxes, and we need to talk about them because they're very important. And YOLO V1 tries to assign the object to the grid cell that contains the middle of the object. Because we already talked about this concept. We just identify the center of the object, and the cell that contains that center is going to be responsible for predicting that object. Using this idea, the red cell on the image to the right must detect both the man and his necktie at the same time. But since any grid cell can only detect one object, a problem will arise here. So to solve this, the authors tried to allow the grid cell to detect more than one object and k-bounding box. So each cell in YOLO v1 was responsible for predicting two bounding boxes, and it's only responsible for predicting one object. So if you have two objects, in this case, the person and the necktie, they're not going to be predicted by using a single cell unless you use a finer grid to separate these two objects. So YOLO v2 introduces more bounding boxes. So instead of using a predicted bounding box of 2, you're going to use predefined boxes for all of the grid cells, and we're going to use k-bounding box in this case, and each grid cell can detect more than one object. So there are two ways of predicting the bounding boxes. Number one is directly predicting the bounding box of the object. That's done in YOLO v1, in which we just predicted the bounding boxes by ourselves. And second is using a set of predefined bounding boxes called anchor boxes to predict the actual bounding box of the object. So those predicted bounding boxes are going to be very difficult to learn. So what if we use a predefined set of anchor boxes and adjust them so that they can better adapt and they can fit the predicted bounding box. So YOLO v1 predicts the coordinates of the bounding boxes directly from the fully connected layers on top of the convolutional feature extractor. But it makes a significant amount of localization error, and it's easier to predict the offset based on anchor boxes than to predict the coordinates directly. So instead of predicting the bounding boxes out of the blue, if you have a predefined set of bounding boxes with different aspect ratios, then you modify them and morph them so that they can better fit to the predicted bounding box, the final box. It's much better for the model to learn and adjust to that bounding box. So in this image, we have a grid cell that's shown in red and 5 anchor boxes for that specific cell, and with different shape and aspect ratios. So in the paper, they called anchor boxes by a different name. They call them prior box. So when you read the paper, you don't have to be confused because they are the same terms. YOLO v2 tries to use the idea of anchor boxes, but instead of picking K anchor boxes by hand, so where did they come from? Like, how do we select these 5 anchor boxes? Instead of selecting them by hand, they tried to find the best anchor box shapes, and these are selected even by their own training procedure to make it easier for the network to learn the detection. We can predict the bounding box relative to the anchor box, and instead of predicting the box relative to the image, which was used in YOLO v1. So using this idea, it will be easier for the network to learn. So in this image, the 5 red boxes that we have seen represent the average dimensions in locations of objects in the Pascal VOC 2007 dataset. So in order to select these 5 bounding boxes, what they did was they used the Pascal VOC 2007 dataset, and instead of using predefined anchor boxes, they looked at the bounding boxes in the training data. So they trained using the Pascal VOC 2007 and COCO dataset. They trained the model, and they looked at the predicted bounding boxes for that dataset. and they run what is known as a k-means clustering, which is an unsupervised machine learning algorithm on the training set bounding boxes, the predicted bounding boxes from the training of the VOC dataset for various values of k, and plot the average IOU with the closest centroid. So they're going to plot the IOU of the different predicted bounding boxes from the Pascal VOC dataset. And by using k-means algorithm, they are going to select centroids and divide these predicted bounding boxes into different groups. So the k-means algorithm is an unsupervised learning algorithm. And for example, if you have a bunch of training data and you put them on a graph and you want to segregate them into different groups, such as predictions on a machine learning algorithm, you can choose some number of centroids, and then by adjusting those centroids by taking the Euclidean distance of the rest of the points with that centroid, you can segregate them into different groups. But in YOLO v2, instead of using the Euclidean distance between the data points and the centroids, the IOU was used between the bounding box and the centroid. So the IOU of the bounding box, of each of the bounding boxes, the predicted bounding boxes, and the centroid are going to be taken, and this resulted in dimension clusters. So those that are on the same group are going to form what is known as a dimension cluster. And they chose k is equals to 5 for the k-means algorithm, and as a good trade-off between the model complexity and high recall. And when they run the k-means clustering on the VOC 2008 and COCO training datasets, that is what they obtained the image to the right. So as you can see on the image, the average IOU is shown on the y-axis, and the number of clusters is going to be shown on the x-axis. And as the average IOU increases, you can see that the number of clusters are going to increase too. And when you group these bounding boxes into different groups, those are going to form what are known as the dimension clusters, and they're shown on the image that's shown next to the graph. The graph on the right shows how much the dimension clusters overlap with the training data's bounding boxes without any manipulation. So, and the image on the right just shows how these dimension clusters overlap with the training data, with the Pascal VOC training data bounding boxes without using any manipulation by ourselves. So using these cluster centers helped increase the mean average precision by 5%. So next we're going to see direct location prediction. Once we have those bounding boxes from the dimension clusters, how do we adjust them so that they can fit the predicted bounding box? So when they used anchor boxes with YOLO, they encountered the issue of model instabilities, especially during initial iterations. Instead of predicting offsets, YOLO v2 follows the approach of YOLO v1 and predicts the location coordinates relative to the location of the grid cell. So instead of predicting the offsets, YOLO v2 just uses the approach from YOLO v1, in which it predicts the location of the coordinates with respect to the location of the grid cell. Last time we talked about that the x and y coordinates of the center point for the object is computed by considering with respect to the grid cell that contains that center, not with the entire image. This bounds the ground truths to fall between 0 and 1, and the network predicts 5 bounding boxes for each cell. So in YOLO v1, we predicted 2 bounding boxes per cell, but in YOLO v2, we predict 5 bounding boxes, which are going to be computed from those anchor boxes by adjusting those anchor boxes to better fit the predicted bounding box. So it predicts 5 coordinates for each bounding box. Last time we have 4 coordinates, one for the center points, x and y coordinates, then we have the width and the height, and then we have the confidence score. But here we have 5 bounding boxes, and each of them will have 5 coordinates, and those are going to be represented by tx, ty, tw, th, and the confidence score is going to be represented by to. And if the cell is offset from the top left corner of the image by cx, cy, on the previous video when we talked about YOLO v1, we used the offset as gx and gy, but here we're going to use cx and cy. And the bounding box priors, which are the anchor boxes, has a width and height of p, w, and ph. And the anchor boxes width and height are given as pw and ph, and the predictions correspond to bx, by, bw, and bh. Now we have to segregate these two because tx, ty, tw, and th are going to be the initial the initial ones that we're going to use, and then the final prediction bounding box coordinates will be given as bx, by, bw, and bh, and we're going to compute them from those values of tx, ty, tw, and th. For example, if we use 2 anchor boxes, the grid cell 22, which is located in position 22, in the image will output 2 boxes, the blue and yellow boxes. And let's see, for example, the dotted ones represent the anchor boxes, and the blue and yellow boxes represent the predicted bounding box. So we need to adjust the dotted black dotted boxes, and we need to adjust them so that they give us the predicted bounding boxes coordinates. Now consider only the blue box, and let's forget about the yellow box, and we're going to have 5 different boxes. Instead of assigning the predicted blue box to the grid cell only as in YOLO v1, because in YOLO v1 we just predicted the bounding box directly. In YOLO v2, we assign the blue box not only to the grid cell, but also to one of the anchor boxes, and that will be the one that has the highest IOU with the ground truth box. So initially, the predicted bounding box, the blue box, is just assigned to the grid cell that contains the center of the object. But here, it is also going to be related with the anchor box that has the largest IOU or the largest overlap with the ground truth box. So we're going to use that anchor box as a reference point, and we're going to adjust it so that it's going to get closer to the blue predicted bounding box. And YOLO v2 uses the equations on the right to assign the blue box to the grid cell and the anchor box. So let's take a look at the equations. So tx and ty are the coordinates, the x and y coordinates. And then we're going to pass them inside the sigmoid so that they can be between the values of 0 and 1. And then we're going to add the offsets cx and cy, because the position of the point, the coordinate for the center point is located, for example, if we consider the top left corner of the image, there is an offset of Cx in the x direction. There is an offset of Cy in the y direction. Then we're going to add the sigmoid of Tx and Ty, because Tx and Ty can be free-ranging values, and we need to make them between 0 and 1 because they're taken relative to the grid cell. And once we add them, then we get Bx and By, which are going to be the coordinates, the central coordinates for the predicted bounding box. And in order to find the width and height of the predicted bounding box from the anchor box, we're going to use the width and height of the anchor box, which is PW and PH, and we're going to multiply it with the exponential function and e raised to the power of TW and e raised to the power of TH. And TW and TH are the values of the previous ones with respect to, so here when we talked about these values, here we mentioned that there are 5 coordinates for each bounding box, Tx, Ty, Tw, Th, and To, and these are going to be optimized so that they can give us the real coordinates Bx, By, Bw, and Bh. So that's what we're doing here. So Pw and Ph are going to be the values of the width and the height, and Tw and Th are just predefined values from the training procedure when we selected the anchor box. So finally, we need the object score or the confidence score. So the probability of the object will be multiplied by the IOU between the bounding box and the object. And then finally, this is going to be equal to the sigmoid of TO. So this is how we get BO, which is going to be the confidence score for the bounding box. Now, we have already covered how to find the coordinates and how do we get the predicted bounding boxes from the anchor boxes. Now let's talk about the output shape of the model. YOLO V2 output shape is 13 by 13 and by k times multiplied by 1, 4, and 20. And where did we get these numbers? In YOLO V1, we only had 2 bounding boxes, and those 2 bounding boxes had 4 coordinate points and 1 confidence score. So we have 4 plus 1, 5 for each bounding box, and then 5 plus 5 will be 10, and then we add them with 20 classes. So in total, we have a dimension of 7 by 7 by 30. But for YOLO V2, we can have a large number of bounding boxes, but here we considered 5 to be the optimal value because for k equal to 5, it's going to be optimal predetermined by the training procedure. And the 4 coordinate values x, y, w, and h, we're going to use those values from bx, by, bw, and bh. And we have the confidence score, and we have 20 classes. So let's say we have 5 of these boxes. So the total dimension will be 13 by 13, then 5 times 1 for the confidence score, 4 for the coordinates, and 20 for the number of classes. So in total, we have 13 by 13 by 125. Finally, let's talk about the loss function for YOLO V2. And the loss function of YOLO V2 is actually more complicated than the loss function for YOLO V1. But let's try to break it down and understand the different components. This function defines the loss function for an iteration t. So for every iteration, we're going to consider the loss function. if a bounding box doesn't have any object, then its confidence of objectness needs to be reduced, and it is represented as a first loss term. So the first term in the loss function is going to try to minimize the loss for the confidence score. So the first part is just basically concerned about that specific task. And as the bounding box coordinates prediction need to align with our prior information, a loss term reducing the difference between prior and the predicted is added for a few iterations. So next, the second term is going to consider the bounding box coordinates prediction and the anchor box's coordinates. And the loss term is going to minimize the loss under the iteration number is 12,800, and we're just trying to adjust those prior boxes or anchor boxes to the predicted bounding box, and as they get closer and closer, the loss value will be for the second term will be lower and lower, and that's what we're doing basically on the second component of the loss function. And if a bounding box K is responsible for a truth box, then the predictions need to be aligned with the truth values, which is represented at the third loss term. And for the third term, which is shown in brackets, and it's the largest one, we're going to basically try to minimize the loss for the coordinate points, X, Y, W, and H. And we need to align them better to the truth values. And the second one is for the confidence score. And then finally, we have the loss function for the class prediction. And the lambda values are predefined weight tags for each of the loss terms. So these lambda values, we have seen them in YOLO v1, and they're given different values depending upon which type of loss you want to use. So if you want to avoid some of the terms, you can just give different values depending on your interest. So that's all you need to know about the loss function about YOLO v2. Now let's compare the performance of YOLO v2 with other detection systems. YOLO v2 is state-of-the-art and faster than other object detection systems across a variety of detection datasets. Furthermore, it can be run at a variety of image sizes to provide a smooth trade-off between speed and accuracy. And the graph and the table below shows how different methods perform with respect to precision and speed on VOC 2007 dataset and the Pascal VOC 2007 and 2012 dataset respectively. As you can see on the graph, the frames per second are shown on the x-axis and the mean average precision is shown on the y-axis. And when we go further to the right, we have higher speed because the frames per second is increasing. And as we go up, the mean average precision is increasing. So the ideal point will be the one on the top right. And you can see all of the YOLO v2 predictions are, mean average precision values are on the top right. And the rest, they might have a lower speed or maybe they have a lower mean average precision. And you could see that YOLO v1 is actually the lowest one, but its speed was actually higher than faster RCNN, so it's found to the right of fast RCNN. And YOLO v2, its predictions, its mean average precision is computed at different resolutions, and these are the points that represent when the input image, the resolution of the input image is being changed. And you can see that the performance for YOLO v2 model for higher resolution 544 is actually 78.6 at a 40 frames per second. And this is actually very, very high compared to YOLO V1, and even fast RCNN. Finally, we're going to talk about YOLO9000. So, what's the purpose of YOLO9000? Like, why is even the title of the paper labeled as YOLO9000 and not YOLO V2? Sometimes we need a model that can detect more than 20 classes, because the Pascal VOC dataset only provides us with 20 classes. And that is what YOLO9000 does. It is a real-time framework for detecting more than 9,000 object categories by jointly optimizing detection and classification. As we mentioned previously, YOLO V2 was trained for classification, then for detection. This is because the dataset for classification, which contains only one object, is different from the dataset for detection, because for classification, we use the ImageNet dataset, and it only contains one object per image. And for the dataset for detection, we used Pascal VOC or COCO, and it's going to contain multiple objects within the same image. In YOLO V2, the authors propose a mechanism for jointly training on classification and detection data. So they said, why don't we mix these classification and detection data together and try to increase the number of classes or the number of predictions. During training, they mix images from both detection and classification datasets. When the network sees an image labeled for detection, we can backpropagate based on the full YOLO V2 loss function. So for example, the model is trained by using both detection and classification datasets, but when we want our model to predict for an image that is intended for detection, we can only backpropagate and optimize by using the full loss function that we have seen in the previous section. But when it sees a classification image, we only backpropagate the loss from the classification specific parts of the architecture, because we have seen the different components of the loss function, and we just only use the part of the loss function which is concerned about classification and not the detection part. The idea of mixing the detection and classification data faces a few challenges. The first challenge is, how do we combine these two datasets? Is there any approved method, or did they just come up with their own method? First, for the detection datasets are very small compared to the classification datasets. Classification datasets like ImageNet has a lot of examples, and detection datasets are much smaller and very hard to label because they contain multiple objects. And detection datasets have only common objects and general labels, like more common objects, and the labels are not very specific. They are like general terms, like a dog or a boat. For example, they don't give you specific information like what type of dog, like what breed of dog are we using, or what type of boat are we using. While classification datasets have a much wider and deeper range of labels. For example, ImageNet dataset has more than 100 breed of dogs. They're not just labeling the dogs as dogs, they're giving them specific names, like their breeds, German Shepherd or Burlington Terrier. They're using more specific names. So as you can see on the diagram below, the COCO dataset uses general terms, and the ImageNet dataset uses more specific words. So to merge these two datasets, the authors created a hierarchical model of visual concepts and called it a WordTree. So they came up with a genius plan of creating a hierarchical model and labeled it as WordTree. And as we can see from the image below, all the classes are under the root, and the root of the graph is going to be like a more abstract term. Let's say the root node is going to be like a physical object, and they trained the Darknet-19 model by using the WordTree. They extracted 1,000 classes of ImageNet dataset from the WordTree and added it to all the intermediate nodes. So they extracted all of the 1,000 classes from the ImageNet dataset, and they just put them as labels for all of the intermediate nodes as we go from the top to the bottom, and which expands the label space from 1,000, which was originally 1,000 classes, to 1,369, and called it the WordTree 1K. So by using more specific terms, because the terms that were used on the ImageNet dataset were more specific, so they just put a bunch of nodes with more abstract terms, and that increases the number of labels to 1,369. Now the size of the output layer of the Darknet-19 becomes 1,369 instead of 1,000 for the classification output. So for these 1,369 predictions, we don't compute one softmax as we do previously in deep learning literatures, but we compute a separate softmax over all synsets that are hyponyms for the same concept. So what is a synset? It's just a set of synonyms, words that have the same meaning, and hyponyms are words that express a more specific concept. For example, if you have a dog, then a more specific word for a dog might be a German Shepherd, because that's one breed of a dog. So that's a hyponym. And we use a separate softmax for each of the synsets that are hyponyms of the same concept. So for example, for the dog, we're going to use a separate softmax for every synonyms or for every word that are under the umbrella dog. And despite adding 369 additional concepts from the original 1,000, Darknet achieves 71.9% top 1 accuracy and 90.4% top 5 accuracy. The detector predicts a bounding box and a tree of probabilities. But since we use more than one softmax, we need to traverse the tree to find the predicted class. Because now we're not just using one label or one prediction, now we're using a tree. So we need to find which class is being predicted by traversing through the tree and selecting the probability value. So we traverse the tree from top to down, taking the highest confidence path. So we start from the root node and we follow the highest confident path. We just select the higher probability values on each level for nodes that are at the same level. And for every split, until we reach a node with probability less than the threshold probability. We're going to probably have a threshold probability, and unless we reach that threshold probability, we just traverse the tree. And when the probability is less than the threshold probability, we predict that as the object class. For example, if the input image, let's say, is a dog, the tree of probabilities would be like the tree shown below. And instead of assuming every image has an object, we use YOLO V2's objectness predictor to give us a value of P physical object, which is the root of the tree. So we start from the more abstract probability and follow the path that has a higher prediction. So how do we traverse? The model outputs a softmax for each branch level. We choose the node with the highest probability. If it is higher than the threshold value, then we move from top to down. The prediction will be the node where we stop. So let's say we have an image containing a dog, and we don't know specifically what type of dog that is. By using this type of method, we start from the root node physical object, then we move to dog, then we move to hunting dog. I think I missed animals. Yeah, there is animals, then dog, then hunting dog. It will stop at hunting dog and do not go down to, let's say, sighthound, a type of hunting dogs, because its confidence is less than the confidence threshold value, and we stop at a hunting dog. So the model will predict and output the value, the probability value of this node. Performing classification in this manner also has some benefits. Performance degrades gracefully on new or unknown object categories. For example, if the network sees a picture of a dog, but it is uncertain which type of dog it is, it will stop at the dog with high confidence, and the output will be a dog. For example, like when we show the image of a dog and the model doesn't know what type of dog it is, it feels confident that it could stop on the more abstract level at the dog, and then it gives you the prediction and the label dog. So the combined dataset was created using the COCO detection dataset and the top 9,000 classes from the full ImageNet release. YOLO9000 uses 3 priors anchor boxes instead of 5. As an example, when we selected the number of anchor boxes, we actually used 5. But in the YOLO9000, 3 anchor boxes was selected as the better option because it reduces the number of output size. It learns to find objects in images using the detection data in the COCO dataset, and it learns to classify a wide variety of these objects using data from the ImageNet dataset. So by mixing the COCO and ImageNet dataset, it learns about how to detect objects using the COCO dataset, and it learns how to classify objects better using the ImageNet dataset. When the network sees a detection image, we backpropagate the loss as normal. We use the total loss term in order to optimize the model. When it sees a classification image, we only backpropagate the classification loss, and we don't use the entire loss function. And YOLO9000 uses the base YOLO v2 architecture, but only 3 priors instead of 5 to limit the output size. Since COCO does not have a bounding box label for many categories, YOLO9000 struggles to model some categories like sunglasses or swimming trunks because it has limits on how many labels or how many categories it has. YOLO9000 gets a 19.7 mean average precision overall with 16 mean average precision on the disjoint 156 object classes that it has never seen any labeled detection data for when evaluated on the ImageNet detection task. So it was a long video, and we learned about YOLO v2 and YOLO9000. And since we tried to cram all of the concepts from both, it took a long time. And in the next video, we're going to take a look at the YOLO v3 model.